Hey, we can get going. Is my audio okay?
Yes, it is.
Thank you. At some point, we will turn off this Zoom simultaneously because there is a lot of trouble with Wi-Fi. So if you by any means can come in person to class, please do. Otherwise, we may not be able to for a very long time offer Zoom, and I have very few people in the class right now. Okay, what we're going to do, it's supposed to have been updated to lecture 8. We are going to talk about features of modern technologies. And there is a lot of stuff that is happening out there now about what do these technology nodes mean? One of the bit dated news from a couple of years ago is about this, that not all the technologies are made equal. So you will find out over here that features in TSMC 16 nanometer, 10 nanometer, and 7 nanometer nodes are a little bit larger than corresponding ones in what used to be called Intel's 10 nanometers. Intel has renamed their technologies in the meantime to catch up with the marketing, but we're going to dive a little bit into this and a little more in the next lecture. But for now, I would like to go through the, how do these modern technologies look like from about 20 nanometers till today. In the meantime, we are recapping stuff that we have done recently at system level. So we have seen that we use Chipyard. We have seen that we can use Chipyard to build systems. We have seen some overview of system level interconnects. Vladimir gave a lecture on NOx. Sophia gave a lecture on what is in a tie link and what's in the coherency and what is in the bus periphery of RISC-V SoC like the one we can build. There is a NOC generator as well. We haven't talked about that. It is in development. It's fairly functional. It's called Constellation. It exists in Chipyard. And you guys, if you're interested, you're more than welcome to play with it or use it as a part of a project. It supports everything that Vladimir talked about and more. But moving on, I have a lot of informative stuff to cover on scaling. So let's get into that. So some of the key points that I'll try to convey in the next 75 minutes are about technology scaling. That Moore's law is slowing down, and but we're still continuing to see improvements in densities in technology scaling. Both logic and memory are continuing to shrink in size, but at different paces that they used to traditionally scale at, and also at different paces from each other, which is kind of interesting and peculiar. That what we are going to study a bit and understand the implications of that. Another big point is everything is power limited now, from even tiny devices to cell phones to data centers. So implication of that is that scaling has gotten us, and the way how we have used or abused technology, whether you would like to use that term, is that we've gotten to a point that we have so many devices that there is no way we can simultaneously power them up at the same time in pretty much any application, and that has implications on how we deal with things. A reason for that is that Dennard scaling has ended 15-ish years ago or a little bit more, and that there is again design implication and technology scaling application of that. Another consequence of all of that is that there is a plethora of technologies that are out there, and not just across the nodes, but even in one technology node, you have a choice of a whole bunch of things that you can do. you pick N5, there is a whole bunch of different flavors of N5. Even if you pick 28 nanometers, there is a good choice of transistors that are in there. You have to make a right choice for the application. And those things are not trivial and not obvious. You need to, perhaps we need to wait till the end of this class to understand exactly how do we make, not this lecture, but till May to realize how we make these decisions. One good news at the end, which we are going to dive into next week, is that all of these devices, no matter in which node they are, how they look like, or which particular flavor they're in, are essentially velocity saturated, and the same type of a model applies to it. This thing better not be. All right, so let's talk a little bit about scaling. So technology scaling simply meant that at the very surface, when we look at the area and the features on a silicon chip, it simply meant that things got smaller. And traditionally, Moore's law meant that linear feature sizes would shrink by a factor of 30%. So whatever was had a unit size in one technology node would have been 0.7 in the next technology node, and that applied to both X and Y dimensions. And as a result, when we multiply 0.7 by 0.7, we would end up with 0.5 of the area, or a half of the area, twice the density. And that has been true for many technology nodes. One thing that we are going to see as a measure, as a measure that has been used until recently, that kind of fell apart recently, is the notion of a contacted gate pitch as a way of measuring technology density. People have done away with it recently, but that simply meant, first, what is a pitch? Pitch is a minimum distance between repetitive features on a chip. So we can measure it from, in this case, the middle of the poly, or we more commonly will measure it from end to end of a poly region. Contacted gate pitch basically means that you need to be able to fit the contact in there. So this gives you some kind of a measure how small is the poly and how well a contact can fit inside. Now, if you look at some of these things, and we'll revisit that later, that contacted gate pitch, as we kept scaling, was holding at 0.7 pace until 22 nanometers. You can see that it is slightly off there. Then, kind of, then quite, this is not 0.7. This is not 0.7, you can eyeball it. So then we got back to 0.7, kind of a pace. So it is skippy. It has been moving kind of in Moore's law's direction, but not quite. We'll talk a little bit about that. Let's recap the NARD scaling rules, and we gave you that paper to read. Hopefully you've read it at some point. It talks about what do the fields, electrical fields inside of a device need to do when we scale the device. So what I've covered so far is the notion of geometric scaling of surface features. The NAR's law, or the NAR's paper basically said that it is not just the horizontal features, the features on the surface that need to scale. It is the whole three-dimensional structure have to scale by the same factor. So the thicknesses of materials and electrical features in the device have to scale by that same factor of 0.7. In order for this to happen, it's not just gate lengths and widths that needed to shrink by a factor of 0.7, but also the thicknesses needed to to shrink by a factor of 0.7. Notice over here that instead of a factor of 0.7, the NARD is using a factor of alpha. Alpha is 1 over 0.7, which is about 1.43. So the oxide has to get thinner every time we shrink the device, but also the electrical features need to shrink over here, meaning the fields inside of a device have to shrink. And in order for, the fields have to stay constant, which means that the voltages have to scale at the same pace as we shrink the geometry of a device. If we were to do everything right in there, the power of circuit would scale down quadratically, the density would go up quadratically, and as a result, the power would stay constant. Now, that has been the case for a while, but not anymore. One of the fundamental reasons, if you read an arts paper where the end of scaling would be, he identified it as the limit to the shrinkage of the gate oxide and identified gate tunneling as a problem. It looked like something that was threatening scaling for a while, but we got away with that. And we essentially had to move to high K dielectrics. If we look at what has been happening with the scaling over generations, you can see spots like these. So when you go, this is showing the gate length scaling from about a micron down to somewhere about 10. This is a bit big to go collected a long time ago. So if we were to follow the NARD scaling, ID SAT, saturation current of a transistor, should have stayed constant. The BDD should have been scaling by a factor of 1 over alpha, or getting smaller 0.7 times every time we switch the device. This is these are some transistor delays. This is some unit delay the roadmaps, and transistor thresholds were supposed to continue scaling as well. There are a few things that have happened over time that derailed this whole picture. Right, if you look at it, like 90s to up to early 2000s, things were basically in check. They were scaling it according to the novel, but it was in the 90s. Then other things happened. First, there was greed. We got greedy. We really wanted higher current off the devices. So that happened. Because that was a way to get higher performance, just drive things harder. And that enabled increase of clock rates and so on. But then this happened is because of the issues with leakages in transistors, transistor thresholds were not as scaling as well as they were supposed to. They quickly got off the air. Now, in order to keep this greedy thing high transistor currents, we have to stop scaling BDPs, and the power problem emerged. Technology people have been working very hard over the past few decades in trying to make smaller and smaller devices. And typically they've been pushing for decades on scaling these horizontal and vertical features. They've been obsessed with these, say, 10 nanometer gate transistors for a while, and we have seen some of those appear. So Intel, even back in 2003, Intel Research was able to make a 10 nanometer gate length device. Standard planar transistor with 10 nanometer gate lengths. What's wrong with that device? Is that the Moore's law device? No. They scale the gate length but didn't scale anything else. So contacted gate pitch, where would be the next device over here? So if you're looking at a gate over here, this is pretty tall, by the way. If you have not noticed. You know, source and drains are fairly close to each other. But where would be the next device? Well, you need to fit this source over here, then there will have to be some isolation. And you have to fit another source over here. So, you know, the other gate, the next gate would have been somewhere over there. This looks more like a 65 nanometer device with 10 nanometer gate lengths, which serves its purpose for papers, publishing a paper, but not for scaling a technology. As we all know, in order to really get to this intelligent value, is to have to switch over to a FinFET structure where you can actually pack everything together. Now, those are not two transistors; those are just two fins, and we are going to see some of the implications of that later. As scaling became more challenging, as we were getting off the Denard scaling trajectory, something new had to be done in every technology node. And we are going to go over some of these things that have been carried over, but here is an illustration on the what has been happening on the timeline since the end of Denard scaling. In 65, which was later replaced with 55, and we're going to talk about that towards the end of this lecture. One thing has been added, that has been kind of showing up in 90 nanometers and 65 in between common, is something that is called the strain. We'll talk a little bit in the next lecture about the strain, but that is essentially the way to manipulate the crystalline structure to crack up the ion of a device. So to increase the mobility and therefore increase ion of the devices. Has been with us since then in every technology people and designers were not willing to abandon. In 45 nanometers, there was a big change. We got off the silicon dioxide as the weak material and switched over to type A metal. That's a big deal. And strain 22, 28 nanometers, which essentially featured a few big improvements. For example, what you can see here, it does not have this little lip on the bottom, which means that we got away with different, better way of building high-k metal gate. Became we didn't have any more replacement heat technology, and this is still the dominant process in the industry today. Probably the largest volume across all the foundries is in 28 nanometers. Of course, we have products that are out there, but 28, if you're designing something, we're going to run to 28. But the problem of leakage became insurmountable. We 28 nanometer device is the last device, planar device, where technology people were able to control the leakage. Foundries like TSMC introduced the 20 nanometer node, planar 20 nanometer node, but it was really short-lived. Designers basically voted it off the island. Nobody wanted to work with that because it was unusable. What happened instead was introduction of FinFETs, and slightly after that, moving to the SR. And the topologies that were able to control the leakages of the device. Now, FinFETs have been changing as well. And they're very different now than they used to be 10 years ago. Notably, what can you tell me about it? Comparing TSMC 5 and 5, and we really don't have really good pictures. They start publishing nice pictures of their pens anymore. But M5 pen here that they showed versus Intel's original pen. Anybody sees any, notable differences? They got skinnier and way taller. This is what we have been seeing in every technology now. These things have been getting taller. Why? Yeah, getting a better hold of the over the channel, so wrapping around that channel to make sure that you turn it out. But also, you get more of a volume to carry the current, so you can keep high enough currents while being able to turn off the transistors. Well, now you'll see you see trouble here. What's the trouble? How does N3 and N2 look like? Anybody see any problem with having a pen that is like that and this tall? It gets hard to manufacture. We are going to run into variations and so on. So changes are again in store. We're going to talk about them, and some of you that may be very fortunate to intern somewhere are going to see to work with these kinds of technologies. Now, another thing to keep in mind, we've been talking about for many years, and most textbooks nowadays are still using channel length as a proxy to technology scale. It really was true up to the mid-90s. And I mentioned this already before. Then we got greedy. Before technology people invented strain, what did they do? To cramp up currents further, on currents further, they ashed the channel. They reduced the channel lengths beyond what was lithographically printable. So, in say, notably say 130 nanometers, 130 nanometer technologies, they would print all the features to be 130 nanometers. But they would trim the gate size. They would just basically sand it down to about 70 nanometers. The reason for that was to get more on current, because that was remember, we needed more on current to keep the main technology driver at that time, a desktop processor, go up in frequency and increase the performance. That kept going down to 65, and then in 45 we had the problem of leakage. Drain to source leakage was a bigger problem than the gate leakage, but this practice had to stop. And the channel lengths have not really. They switched from a different slope. We don't have exact data now, but if you look at these N5 devices, they're about 15 nanometer channel lengths. So it may look completely crazy, right? You're talking about 5 nanometer technology, and the gate is 15 nanometers. Does that make any sense? It does if the density corresponds to what would have been a 5 nanometer technology in planar fault. Now, people can totally make, like Intel was able to make a 10 nanometer device, back around 2000. People can still make these FinFETs to shrink down to sub nanometers. They did it like 15 years ago. But this is like not the most one device whatsoever. They just made one roll with a channel length of 5 nanometers. It does look like a transistor, but it's not what it's supposed to be. What are we going to see instead? And we have seen quite, some of these previews a few years ago, and that is now more apparent in the roadmaps. So, planar device, and by the Global attended Jim Keller's part of the colloquium that he's been shown for the first time about 2 years ago, 2.5 years ago. The platelet infects, and then that is expected to be replaced very soon from late next year and on with something that is called nanowires and nanosheets. The basic premise here is instead of trying to make these things taller and taller, we're going to just basically technology people the whole. And those wires can be turned on and off, semiconductor wires. So here is how the current roadmaps look like. It is not the quest of making shortened channel lengths. It is the quest of scaling the area, controlling the power, controlling the leakage, and maintaining the cost to be reasonable. Remember, one of the fundamental premises of Moore's law that I mentioned in the first lecture that is being violated at the moment is that we are supposed to pack twice as many devices, twice as many features in every technology node, but the wafer cost is not supposed to go up by much. It has been, the wafer cost has nearly doubled in recent technology nodes, which means that the transistors are not getting any cheaper, or they're getting slightly cheaper. Okay, so what are we going to do to continue scaling the density? And this is the roadmap roughly for the next decade or so. These nodes, technology nodes, are going to be slightly more spaced. They're not going to get a new technology node every 2 years like we are used to. They're going to get a lot of these intermediate nodes and flavors of different technologies. And the actual new technologies may be spaced about more like 3 years. And, most companies are talking about that. And we are seeing actually at this moment, TSMC has delayed by 9 months. Introduction. So here's what they're looking at. Benefits in these nanometers, in these technologies that correspond to roughly 3 nanometers. So the Samsung has been saying that they're going to switch to 3 nanometers to nanosheet. To start the thing that I've shown. One big thing that is going to have impact on all of us, and it has been, there has been a lot of investment here, is somewhere in the next couple of years, they're expected to see very power limits. I will not spend a lot of time because we don't have enough data to talk about it, although there have been quite a bit of evaluations that we've seen. As we are shrinking transistors and they're getting taller, and as we are shrinking standard cell heights, since each transistor can carry more current, we are shrinking the number of pins and fingers in the device. So that if you look at the very bottom, that the standard cell area has been shrinking because each device has been getting taller to carry more stuff. So it's becoming more three-dimensional. And one of the big problems, if you look at these 3 nanometer standard cell, 5 and 3 nanometer standard cell, a lot of the area goes into power rails, like a lot, 30% or something like that. So how about we do this? Why don't we just bury those power rails like PG&E is supposed to do with our power rails, put them underground, and that's what they are working on. This is really, according to technology people, is not very difficult to do. It should have been done at some point in the past, but like PG&E, they've been postponing this because they didn't really have to do it. Essentially, we define trenches like to define pressures for isolating devices already. And instead of filling them with, silicon dioxide, we fill them with some kind of metal. And then instead of going up for your power for standard cells, you go down and tap. It's a little more complicated, I say, because this is a relatively high resistance metal that is being buried down there that plays nicely with silicon substrates, and we'll see how it works. But if you just imagine, there is like 30% of decaying by burying that stuff under the place. And it's a deep implication on the design, and we're going to see how that play out. I know that a lot of people are busy now trying to evaluate and build these standard cells, evaluate, find best ways. Again, anytime there is a disruption like that, it's an opportunity to jump on it and do something. For example, there are models out there how this would look like. If you come up with a meaningful density study based on the models, you can publish a paper in one of the leading conferences. There are two other things that are happening over here. You've seen NMOSes and PMOSes separately. They have these other structures that are port sheets that you can put basically a button of devices without having to separate them, as the definition of a subcontroller. So you're going to be hanging off the head here. And then you can mix them and match them, these complementary FETs. We'll see how much of that plays out and how much of that makes sense. For this to make sense, I think these stacks of sheets are going to have to get quite a bit taller. It is hard to see to have visibility more than 5 years down the line of what is going to happen, right? We may be going like TSMC went after 20 nanometers node and have to back out. Nobody wants it. So we'll see how these things play out, but certainly technology people. So there are the pictures of what people have done. Very power and stuff like that. They are not picky, by the way. These pictures, but hopefully don't make them pickier. Pickier means less roughness, less variations in resistance and so on. And these are different flavors of pictures of people that made for complementary transistors. Okay. Any questions about this? Yes.
So this thing is designed by this over again like not scaling.
They're not scaling in it because we could not scale transistor thresholds anymore because the source train linkage was getting to be too high. And as a result, because we care about performance, we can scale the supply voltage. As a result, power density stopped being constant until it started going up. Power density at the moment, if you look at it, where compared to where we are supposed to be, is at least 10 times larger than it was supposed to be. According to that, because we have lost about 10x. We jumped up about 10x. What does that mean? And how is that possible? How are we not knowing everything that we make? And 10 times is a lot. This class basically will deal with that. Power management became the big thing. So it has been, the buck has been passed to the designers. Technology people have thrown their arms up in the air and says, designers, you asked for this, you deal with it. Okay? All right. So there are, so continuing with the pitch scaling, what we had mentioned before, and how does that make less and less sense over time, but we're going to see where we got with that. This is Intel's 45 nanometers, 32 nanometers, 22, 14, and 10. Usually, Intel was really practicing Moore's law. So they were going at 0.7 all the way to here. Clearly, from 32 nanometers to 22 nanometers, it was 0.8. That's the pitch scale. We call it pitch scale. Or 0.8. What happened with 22 nanometers? They switched to FinFET, and we don't want to push our new technology completely too hard, so they made some compromises. Similarly, going to 14 nanometers, 0.78, down to 10 nanometers, it's also 0.77. It's clearly not 0.7 anymore. It has been hard to do these. The scaling of dimensions. But what we have seen here is they've been playing other games. Vintage has been scaled aggressive, about 0.7. They have added in 14 nanometers local interconnect, which is called metal zero, that used not to exist there to connect, to drop directly onto gates and drains. And then they couldn't scale metal 1 because metal 1 had to stay about the same pitch as the gates. The things that go into fence, like metal 0 and metal 2. One metal goes in the direction of fence, the other metal goes in the direction of gates, the holes. They're scaling aggressively. So they came up with a metric of contact voltage times the densest metal pitch. Multiply those two, and you end up with exactly 0.5. And that was their claim that the Moore's law was alive and well. Why does this matter? Is because that was the rule that was applied to scaling standard cells. And majority of the world are test runs and standard cells, so everything was okay. Here's another interesting thing, is when you look at the comparison of 14 nanometer equivalent nodes, and this is a bit dated, this is a few years old, 2 years or so old, but the last time when I could get these on one sheet and all of them were willing to say what were their pitches. So thin pitches between the two technologies for now this one. Intel had the most aggressive thin pitch. There's an important metric over here of 1/3 of a thin pitch is essentially, if you look at the contacting things, that's supposed to be a representation of a technology. So this is really representative of it. Deep lines in Samsung were about 30 nanometers, 24 nanometers in Intel 14. EECS 16 to 33. Contact with deep pitches were the most aggressive in Intel. And that was very well measured at the minimum S1 cell size. Now, if you compare these technologies, all what you can carry away from this slide from about 2 years ago is going down to 7 and 5. What each of these technologies meant was that there simply was not created equal. Whatever corresponds to Intel 7 was off the chart for Samsung. Samsung 7 was like Intel's 10. TSMC's 7 was like Intel's 10. So what was the consequence of this? Intel renaming their technology nodes. What used to be 7 nanometers is now Intel 4. What the technology that we are working with is Intel 16, which used to be called Intel 22, and so on. So you need to catch up in marketing. But the other consequence is that the density is not exactly what it's supposed to be, and we have lost about one technology. It's not terrible. Over the past decade, we've lost about one technology node, and our power densities have gone up by a factor of 10. But no reason to panic. They're going to convince you later on. So this is more of what is happening over there. More recent pictures are showing that Intel is finally lagging in 2019. Intel was actually lagging compared to, no matter what these numbers are mean and how the technologies are made, their system cell size was behind in their 7 nanometer. We'll see how these things are going to play out in the next couple of years with aggressive Intel's technology push. But TSMC is now well ahead of the game. If you look at it, where the features are, they're about 2 years ahead. Now, this is another thing that I have mentioned before. Where is the volume? So these are all the nodes that Intel, I haven't looked at them what was published this year, but last year, here is where Intel's volume was running, where the paths, what the paths of them. The largest wafer revenue was in 7 nanometer node. But the largest volume was, they haven't published, but most likely 28 nanometers. So, because remember, 28 nanometers is about 4 times cheaper per wafer than 7 nanometers. So it is likely the highest volume still running through 28 nanometers. But you can see more advanced nodes where if you look at this system, volume manufacturing just ramping up to 5 nanometers, which were the leading cell phones, essentially. But the most money will make about 7 nanometers, which is where you would find volume. I think basically Apple and maybe Huawei were switching to 5 nanometers. Majority of the volume was NVIDIA, AMD, previous generation Apple products, and the rest at 7 nanometers. And then all the Wi-Fi and everything else that is out there was in 28. All consumer products, all storage, and etc. was in 28 and starting to shift to 18. And there are a few people who are still stuck in 29 because they connected their products and couldn't get it out. Okay. The technology that we use for educational purposes here is ASAP7. That is none of the above, but is kind of an idealistic technology that represents something that corresponds to N7. Here is a summary of what it has. It has 9 metal layers, which is on the low side, but perfectly good for fast projects. And it is showing these 10 pitches that are pretty aggressive that correspond to the most aggressive 7 nanometers that we have out. Another thing that I wanted to very quickly mention here is that in each node, including the 2832 that you see out there, we have a good number of different transistors because different applications may have different needs. For example, we are looking here at 3 different devices that exist in Intel processes, in Intel's 32 nanometers. One, high performance or standard performance, have one particular gate pitch of 112 nanometers. If you go to a low leakage version, the transistor gate lengths are getting longer. Although the standard cells and everything has not changed, the transistors that get instantiated are actually larger, and that helps with that. They have higher thresholds as well, so as a result, they have less saturation current. And you can see this trade-off. If you're trying to design something high performance, you have to have lower threshold, get higher current, but that device leaks. And you have a limited number of those that you can throw down. If you're going for low power, less leakage, you have less on current, and it's going to be a little bit slower. And then there are IO devices that behave by completely different rules. These numbers, we don't have exact changes, exact numbers here, how these things look like. N7 and N5, which is over here from the blue is N5. This is and blue line is N5, red line is blue line is N7, blue line, red line is N5, and the black line is N5 plus. So N7, N5, N5 plus. You have a choice of 1, 2, 3, 4, 1, 2, 3, 4, 5, and so on. Different transistors in each technology. What you'll find out, although the standard cells look exactly the same, layouts look exactly the same, physically the device is slightly different. It has different dopings, different thresholds, and sometimes slightly different channels as well. Two other things that I wanted to mention here. Resistances of devices of their source and drain regions, as we have not been able to keep up with scaling them, have been going up. So resistance to go from a contact to the source to this drain extension to reach the channel has not kept up with the scaling of channel lengths. So essentially what we have here is this. So we got the parasitic transistor. What does that mean? What does that mean for designer? That we get this resistor for free? Do you like that resistor? It's a source regeneration. You got source regeneration for free that you cannot get rid of. What does that mean in digital world? What is it telling you about? What does this is RS, so that means that if you're in Allen world, this is 1 over, GM is equal to 1 plus GM RS. The overall transconductance, or the gain of each of these transistors is less. You're losing intrinsic gain. Things look really bad. What is the intrinsic gain in scale processes? So when I was a student, there was a good number to remember. Intrinsic gain of 100. That is basically what you could get out of these older technologies. What is it now? So at around 28 nanometers, it was sitting at 20-ish or so, slightly below. 20 nanometer node was bad. It was dipping to like 10-ish in some of the nodes, and certainly there are was where you have an intrinsic gain of a device of 10. It's hard to be an hour designer there. Things are better with FinFETs. They've jumped up back to like 20, but these resistances, parasitic resistances, are threatening that. The other thing that is a problem here is that there is a whole bunch of capacitances in there between the gate. Right, I mean, we would like to apply the field, a voltage to the gate, and we would like that voltage to translate into the field that is controlling the channel. So if I put some voltage here, I would like basically to have all of that voltage control the capacitance between the gate and the channel. That's what we turn it on and off. But instead of just doing that, we get a whole bunch of parasitic capacitances that are looking worse and worse, and they look pretty bad. Essentially, the parasitic capacitances, the lateral capacitances, the contacts, and so on, have been more than 50%, which means that the efficiency of the voltage that you apply on the device is like a half or less than half. So instead of just turning on and off the device on and off, we are moving everything around. That's all for the first part that I wanted to cover today. Few announcements. There will be no lecture on February 22nd. I think some of you have asked about that. We don't want an overload for anybody that week because we do want your project proposals that week as well. So go to SSCC if you are short of ideas and think of something that you've seen there to formulate as a project proposal. We're gonna also post an assignment this week. This one is not going to be very lengthy, but we do want you to get going with some problem solving. We have a lab 3 that is due this week. We have gotten to a lot of stuff that is usable for building things. Lab 4 is a little more intense. It's like a lab and a half. So you get 2 weeks to do that after SSCC. The idea of all of these, and there'll be, I believe, only one more lab, 1 or 2 more labs. These are teaching, bringing everybody to the same page of design flows that we use for physics. Instead of everybody learning on their own from senior grad students how to do things, you just need to go to 6 labs and hopefully you retain all of that. A beautiful thing of you've seen Hammer in this lab. Hammer has plugins for all other technologies that are in use. So if you take out a sub 7, put Intel 16 or TSMC 28, it just works. Okay. The next thing that I want to cover are implications of lithography. And we have heard a lot of that, and that is something that affects designers. Designers need to be aware of what lithography does to us. Any questions so far? How was? Yeah, it's a good question. They have changed their shape. So the question is, how are the vias scaling? They've changed their shape. If you look at with tinted processes, instead of, before that, we had these nice square vias that people have gotten used to. In tinted process, we started seeing more like these wedge vias, so more like rectangles and more like looking like that. That is also an implication. The implication of that is this different scaling of different metal layers. So in certain metal layers can push the pitch. Those that get the short side of the via. Those that get the wide side of the via, we can't. but we can design standard cells and other things around that to exploit that. Good observation. Yeah. People got that, and then you need to make your things, your layers asymmetrical to take advantage of the edges. Good question. Okay. Lithography. So here are a few key points that I'm going to try to convey. I conveyed many of the key points already about the technology scaling. Here is what we're going to try to get in the next 20 minutes or so. Lithography restricts features in the design and affects variability. Designers need to be aware of that. No matter what kind of a product you're designing nowadays, you'll find out that variability matters, and you will end up spending quite a bit of time, no matter what kind of a product it is, understanding how well the actual physical product reflects the model, and how does variability play a factor to that. We'll have a special lecture on that, but for now, we want to understand some of it that is due to lithography. All the lithography that is deployed now is optical. However, it was true up to 2 years ago or so. Now we are seeing some deployment of EUV. EUV changes things. We have seen deployment of EUV in 5 nanometer technologies, but it is limited. It is only a few layers are done by EUV. The rest is done by standard optical stuff. EUV has been coming since I was a graduate student. It was like just 2 more years and EUV is going to save us. So, but finally, 20-something years later, EUV is here. It is more expensive. It is not going to be everywhere, and it is not going to displace a lot of the systems that are out there, but it helps in these really small technology nodes. So let's take a look at a few things that are common for everything. So here is a typical lithography system, which is step and scan. And I'll bring it to the next lecture. A physical wafer and a physical mask. There is a projection system. This is a big, really expensive lens. Over here, there's a mask that we shine the light through that projects a picture of your layout onto the wafer. Mask moves in one direction, wafer moves in the other direction. We are never projecting through the entire mask because it would not, that nobody has made a lens like that. We are only projecting a slit of light, and we are scanning through that mask. So essentially, you're shining a slit of light through the mask and scanning it across. It projects in the other direction, scans on the chip. It's like photocopier. We don't photocopy at once, we scan it. Scan it. There are many things that to align precisely. We'll see that some of the layers have to be split. This alignment is really important, but if things are slightly misaligned, there are no things that are perfect in this form. That shows up in the design, and designers need to be aware of that. Let's get to the bottom of things. People used to change the source of light for optical lithography. There were different lasers that were used for this scanning to shine the light to the mask. And then they ran out of resources at 193 nanometer wavelengths. A wavelength of argon fluoride laser that is deployed all over the place is just basically 193 nanometers and has not been shrinking. But we really wanted to shrink a bit the sizes. This has been a problem. Like we have been trying to take these pitches that are really, really small, that are much smaller than 193 nanometers, with a wavelength of light that is much wider than that. So, somebody will say we are trying to draw 1, centimeter lines on a canvas by using a 3 centimeter paintbrush. So that it's kind of hard, try doing that. there are certain things that you can do, but you can't pull off any 1 centimeter feature on a canvas with a 3 centimeter brush. And why is that? Remember your high school experiments. So when you shine light to a slit, the slit is comparable to the wavelength of the light. What do you get? You've done that. You had a laser, and you're shining a laser light through a pinhole. You get what? Remember the rings and lines and stuff like that. So you get this. There is a lag over here in my Zoom, but I tried my best. So there is a light intensity that corresponds to these rings, circular rings around the pin. There is some resist that is being put on the wafer, and what you want to do is to exceed some resist threshold. Oops. Back. Okay, this is not cooperating today. Some resist threshold needs to be exceeded in order to expose it and be able to remove it or retain it on the wafer. So this will define your line, whether it's a gate or something else. What happens when you shine a light through slits next to each other? Start getting those interference patterns from high school physics, and things may look like that. So depending where are these two slits with respect to each other, they may constructively or destructively add. Meaning the light will add or subtract to each other. So depending, some of the features will be amplified. It will also affect the definition of a line. Depending on where they are, the two neighboring lines may be thicker or thinner. It's kind of a problem, right? If you would like a particular transistor length, you actually mean it. You want a transistor of minimum length and not minimum length plus epsilon, depending on its proximity. So the rules exist for that. One of the rules that often puzzles people are these thin density rules or polydensity rules. Basically dictates that the things need to be at certain density because lonely transistors are going to be thinner. Will have shorter channel lengths than those that are not printed in isolation. When we are printing things in sub-wavelength, one thing to notice is the wavelength of light. It doesn't define the features here. Depending on how much light I shine versus the sensitivity of this resist, I can have a thicker wavelength or thinner, right? But it defines the pitch because I need to put these at a certain distance from each other, and that distance is set by the wavelength of light, nothing else. How are they going to constructively or destructively interfere with each other? So the length, I can do whatever I want with the length, through the exposure, through ashing, through whatever, but pitch is set by physics. So that there is no way going around that without shrinking the wavelength of light. And it has been really hard over the past 30 years. They haven't got it. So generally, when you look into lithography, the big thing that is defined is so-called critical dimension, which and critical dimension traditionally over time has been defined as the half of the pitch. Typically, when you look at in older design rules, poly length was a half of the pitch. So that's why traditionally CD has been defined as half of a pitch, although that is not really true in modern processes. So critical dimension, if you look at these lithographic equations or or consequences of our high school physics, it will say CD is equal to some constant K1 times lambda over the numerical aperture of the lens, the projection system, and lambda is the wavelength of light. So it is somehow proportional to the wavelength of light times a few parameters over there. And K1 has a theoretical limit in current systems of 0.25. Numerical aperture is n sine alpha, and here that is set to 1. So this critical dimension is somewhere larger than 50 nanometers, meaning that pitches that are less than 100 something nanometers are impossible to make in one pass. You can't make them in one pass. So how did we get to this? Well, decreasing lambda, people have been trying, many billions of dollars in environment. There's been work with advanced light source and so on up in LBML, moving towards extreme UV, but it took a long time, so it has not been shown. The other option is to try to increase numerical aperture. Well, getting science to exceed 1 is kind of hard. So the only chance is to do something with this n, but projection for air limits it to 1. We'll see, the so-called immersion lithography that's shrinking K1 is essentially working on this projection system, but often people will tell you the limit is 0.25, and people have gotten closer to what that have to do. So, if you look at Intel's pitches here, here's what happened. Over here are beyond the resolution. And one thing that industry has noticed, they picked home pitches that, by the choice to be more aggressive with TSMC or Samsung, has forced them into going to making multiple passes at each layer sooner than the others, and encountered various sources of variation as a result, and well-documented 10 nanometer node yield issues. If they just relaxed it by 10 nanometers or so, or 5 nanometer pitches, everything would have been, easier. But they bet at that time that the lithography was ready, and it was not. And that cost them 2 years. And falling behind. So let's take a look at what we can do in lithography. We can do a few things. Each one of them has some implication on design. We can do immersion, off-axis illumination, optical proximity correction, phase shifting masks, multiple patterning, and in the end, EUV. First, immersion was a crazy thing that happened 20 years ago. This whole thing lives in a clean room. We are very, I believe some of you have been and seen a clean room, at least in university clean room. So we are supposed to be operating in this clean environment. There are supposed to be no liquids whatsoever. Everything is operating in clean air. There are no dust particles and things like those. And then somebody says, well, in order to increase my numerical aperture, how about I project this to a droplet of liquid? So this whole thing, very fast litho system. Remember the mask and the wafer are moving in different directions. Let's just do that in water. People thought people are insane. food products came up and everybody is doing immersion lithography nowadays. So there's a droplet of liquid on the bottom. Used to be some kind of water. Now are more like glycerin type of things because they have better, even better refraction coefficients, and life is good. They're easy early artifacts, and some people have shown that, you know, a bubble of air with print on the chip, that's not good. But they've gotten found out. The second thing is getting closer to this 0.25. And the issue of modern or any projection system is this. You know, this is like a camera, any of you amateur photographs. So if this is your projection system, and here is some kind of a light source. Let's move this up there. This light source has an opportunity to shine a light in every direction. So as it goes through your lens, you can choose to go directly or bounce off the sides. What happens? Well, this is multiple, this path that the light traverses is multiple wavelengths. And when these things meet down on the wafer, they may constructively or destructively add or subtract. So that's kind of not good. Depending what I'm printing, I may end up, you know, with different intensity of light on the bottom, which would affect the resolution. So what do? Most of these systems block the direct path. And depending on how much they block it, well, if you block the direct path, then everything is going to go and add appropriately on the sides. So these off-axis illumination things, which means, you know, there's angular, but this kind of rare, you mostly have odd and dipole. What's the implication of this? That certain directions or angles are favored over others. So, sorry, with either of these features, there's no 45 angle lines. And if you go with this, you can only have vertical ones, no horizontal ones. Well, you can have horizontal ones, but they're going to be wide, not as many. So we just have to live with that. That is the reason why we have preferred or forbidden orientations in our layouts. So your poly can only be, you know, up to 65 nanometers or 90 nanometers. You can draw whatever you want. It will make it for you. No such thing anymore. Your poly has to be vertical. Your pins have to be horizontal, and no discussion about that. You get the DRC error if you try to do anything else. The other huge thing that has happened is resolution enhancement. This is showing that in 120 nanometers, you can get without resolution enhancement or optical proximity correction, you can't do, you know, you can still get usable arrays. In 90 nanometers, starting to dicey. 65 nanometers, you get nothing. You could project things without optical proximity correction. What does this mean? So if I am trying, if I draw this in my layout, and I shine a light through it that has a comparable wavelength to the feature that I'm trying to print, what do I get on the wafer? Or something like this. But that's not what I want. I want my nice looking transistor. So in order to get this, what do I need to shine? What do I need to draw? A dog bone. approximately, and I didn't draw it nicely. It may have to have some assist features over here and there. But they don't do that. I mean, you guys, some of you have done layout, and I'm sure you have not been drawing dog balls in these assist features. That's done behind your, after you're done. It goes through the OPC software. OPC software adds all kinds of features to it, and then factors it, and the maths is written to incorporate all of these features. It's a lot of work for the software. The number of features compared to what you've drawn, from what you've drawn to what is being made on a mask is blown up by about 100x. And that's compute time. That used to be a challenge, and Berkeley students saw that as an opportunity back in the 90s and started the first OPC company. We made good money out of that. OPC algorithms have been changing a lot, and there are companies, every few years when these, current algorithm runs out of juice, somebody comes up with an idea of making a better one, and that's what has been happening. So every time you see a challenge, somebody sees an opportunity to make something better. So, people used to live down to 45 nanometers with light OPCs. Then contacts have been particularly nasty to print. Nice square contacts of these bar contacts, wedge contacts, I think. 50 difficult because they're really the small stuff. This is how it will look like with a normal OPC. You basically build a diffraction pattern so that amplify certain features. And then going down to 14 nanometers and 7 nanometers, you have a lot of stuff down there. And you're essentially doing so-called inverse lithography technology. You don't have to worry about that, but there is an implication to the layout that are these crazy design rules that it's kind of hard to understand why there is a certain design rule. Well, because these guys need to fit in their stuff over there, and you can't have your stuff if you want all these features. So inverse features if you want. I have quite a bit more stuff. I'll have to pause it over here. One thing that has been a savior here is extreme ultraviolet lithography. Lambda is suddenly goes from 193 to 13.5 nanometers. So life is good. Design rules now, when you look at these N5 and N3 nodes, are suddenly simpler. Way simpler for transistors and fins. They're still very complicated for middle metal layers. Why is that? Because they're done still optically. Why they don't just replace everything with UV?
It's longer.
UV machines are slower, a few times slower, way more expensive. So, and designers already know how to deal with optical, so we're just push this to designers. You guys, the life is that that these middle layers are going to still, or everything up that is non-critical is going to be done optically, and you're going to deal with that. It is in production in basically bottom layers. Transistors and vias are done by UV. Okay, I'll pause here. Any questions? We'll continue next week.